We love a good branching algorithm, and we've implemented a multiple of them in Houdini, like space colonization or diffusion limited aggregation or graph bundling. But looking through some of my old setups, I found one technique that we somehow haven't covered yet, and that's really simple and fun to implement. So let's just do that. Before you start, this video is brought to you by our patrons. More info at the end of this video. First of all, let's talk about the principle. Let's say we want to create a branching structure that looks like this. It links one starting point to two endpoints and has a branching point somewhere around here. To get to that result, we can first of all start out with the simplest graph that we can think of. Just a straight line connecting our two endpoints to our single starting point. And then we're going to take those two lines and we're going to turn them into Vellum objects. We want them to act like strings pulled taut. So there's a bit of tension on both of them. And then we're going to take a look at which points are close to each other, for example these two. And then what we're going to do is we're going to spawn a glue constraint between those 2 points. And in the next step we're going to take this glue constraint and just set its length to 0, basically pulling both of these points together into one point right here. And what this now did is, well, it pulled the next set of points here closer together, close enough so that we can spawn a glue constraint between these two. And we're going to do the same thing. We're going to pull them together, which then moves these 2 points close enough together. And in the end, what this will do is it will basically make this right here, those glue constraints, travel along our 2 lines, basically like a zipper pulling them together. And this will run until we reach a equilibrium point where the stretch stress in the whole system keeps those points far enough apart so we won't spawn any glue constraints in here anymore, and this will sort of settle in this resting position right here. And we can do this with 2 lines or many lines to get nice inorganic structures. And the best thing about this whole system is that we can do all of that logic just with a single glue constraint node inside a Vellum solver. So let's build that. Starting out in an empty scene, let's drop down first of all a geocontainer, let's dive inside and let's first of all create a branching structures. And the branching structure that I want to build here consists of one point right here in the center and then a ring of points around it, which I think just leads to really beautiful and organic looking patterns, sort of inspired by the bottom of lily pads, if you're interested in that. But let's first of all create a single center point just with an add sub. And on the add sub, you're just going to create one single point at 0, 0, 0, right here. And then let's create the ring of points around it. And for this, we're going to use a circle. Let's make this lay on the XY plane like this. Let's give it many divisions. In my case, what worked nicely is 128. And let's turn this into single points by again using an add sub. And in here, instead of creating a single point, I want to delete the geometry but keep the points. And now I have this ring right here. Next, I want to draw the connections from the center point to each one of the ring points around it. And for this, I'm first of all going to merge both geostreams together. And in here, the order in which I wire this in actually matters because I want my center point right here to be the first one in this merge node. And this is for the simple reason that I want this first point, the center point, to always be point 0. And I get this by wiring this in first. I want this to be point 0 because next I want to drop down a point wrangle. And there's going to be a little bit of vex involved, but there are going to be very small expressions. So I think you should be fine in here. And I want to have this point wrangle run over all the outside points, but not the one inside point. So in the group field up here, let's just say exclamation point 0, excluding the first point in here. And for every outside point, I want to add a new primitive, a new polyline. And this polyline should be on geostream 0. It also should be of type polyline. And now I can finally specify the connections, and the connections will always be starting at point 0, so a midpoint, and then the point on the ring that we're currently processing, which is at pt_num. And now I have this star shape right here. You could generate this particular star shape with many different strategies inside of Houdini, but this is just the most general, and we're later going to also exchange the input geometry up here for some more interesting patterns. So yeah, This is the route that I went with here. But taking a look at our point display, we currently just have one point in the middle and then a bunch of them around there, which is not enough for a Vellum simulation. So let's next resample those points or resample those lines. And in here, I want to specify a fixed number of segments, and let's just put in 64 like this. This worked nicely for me. Now, what this resample node also did, and this is something that you should always keep in mind if you do some resampling, is it split our midpoint and created unconnected lines. So if I drop down an exploded view right here, now all those lines are not joined anymore. If I were in the node before it, they are all joined. Now they are unjoined. However, this is good for us because later on the glue constraint node that we want to use inside our Vellum solver expects these to be separate geometries. So again, this sort of little thing right here is actually useful for us here. Next, before I want to turn this into a Vellum geometry, I first of all have to specify some pinpoints as well. And I want my center points to be pinpoints and my outside points, my ring points to be pinpoints as well. So how can I define them? Well, if I take a look at the point display and maybe compare a point like this in the middle to a point like this at the edge, the one difference between those is the number of neighbors. A point in the middle of a line always has two neighbors, and a point at the edge has only one neighbor right here. And we can use that to differentiate between those 2 points. And we can use this in a group expression node like this. Let's wire this in. Let's make the field right here a bit bigger. Let's set the group type to points. Let's set the name to pins. And in the vex expression, again, we want to check the neighbor count of each point. And this takes as inputs, first of all, the current geostream and then the current point that we're processing, so add ptnum. And then we simply want to check if that point is not equal, so exclamation point equal to 2. And once we do that, we have all the points right here on the outside grouped and also all our points here on the inside grouped as well. So with this done, we can turn this into an actual Vellum geometry. First of all, by dropping down a Vellum constraints node. And in here, I want to keep the very simple distance along edges constraint. So just stretch constraints between each point. And the default values in here are also all fine. The only thing that I want to change in here is the rest length scale, because again, I want to add a bit more tension to the simulation. And so I'm just going to set this to 0.5. Make the goal length of each of those constraints half as long as their starting value. And then we also need to implement the pins. So another Vellum constraints node. Let's wire in all 3 inputs in here. And let's set this to pin to target. And up here under the group, I want to specify points. And I want to specify my pin points. And this is all I want to do in here. And finally, we can drop down a Vellum solver. And I want to just play what we have right now. And we have a little bit of a droop right here on our lines. So I think this is looking proper. What we should do next is, before we're going to implement our logic inside that Vellum solver, is we should make the Vellum solver itself a bit more simple. So first of all, if we take a look at our collisions in here, for this type of simulations, we don't need any collisions at all. In fact, they're going to, in the end, sabotage the effect that we're going for here. So let's just disable all collisions. Then let's go into the forces and also disable gravity. And what you might also want to play with is the velocity damping to make the simulation in the end a bit smoother. But at least for this, I left it at 0. And now with this set up, we can finally jump inside of our Vellum solver and implement our glue logic in here. And fortunately, again, this is really simple. This is just one new Vellum constraints node that we're going to wire into the force output, because this sticky node right here tells us this is where this node goes. And on this node, first of all, I want to create constraints each frame, not just on the creation frame. And I want to create glue constraints. Now I want to create those glue constraints between points. So let's set both the starting geometry and the target geometry to points. And let's add a star in here to just search for all points. Then I want to specify my glue search. And the main thing that I want to change in here is the max search distance. And then also the constraints per point. So how many lines we can glue together. First of all, let's set the constraints per points to a fairly high value, let's say 20. And then let's deal with the max search distance. And I want to animate this value because in my experience that left me with the most beautiful simulations at the end. So to animate this, let's first of all go down here to our auto update and set this to manual so it can freely scrub in a timeline without caching anything. And let's go to the first frame and set this to a very small value, just 0.01. Set a keyframe in here and then jump to the end of our timeline and let's try making this just 10 times as big. So 0.01, like this. Now with this animated, we can again jump back to frame 1, set this to auto update again. And the final thing that we need to do is once we create those glue constraints, we want to pull them together. And we can do that by simply going to the rest length scale and setting it to 0 like this. And now this should be all we need to do to get this working. So let's keep our fingers crossed. Let's hit play on our timeline. And sure enough, we get a pretty beautiful branching structure. And of course, you can play with the max search distance value in here, the maximum value that we assign in the end. You can also play with the amount of stress that you're giving each line in here before simulating, so the rest length scale on our distance along edges constraint. And between those two values, I think there are a bunch of really beautiful patterns hidden in here. Let's jump out and let's maybe try another pattern. Up here, I'm just going to wire in a switch node. I can try out different patterns. And I'm just going to bring one in that I built earlier. And it's going to be this geometry right here, where I'm starting out with a sphere, then cutting away the lower half, then scattering a ton of points on there, and then jittering those points a bit to get this sort of point cloud in here. If I merge this together with my center point and draw a ton of connections to these upper points, I should in the end get a geometry that looks maybe a bit like a tree or like a shrub or something. Something fairly organic. So let's try that out. Let's go into our Vellum solver and let's hit run on this. We definitely do get something that sort of represents a shrub or spider webs or something like this. Fairly organic, fairly beautiful. Now, the only thing left to do for us here is to smooth it out a bit. Let's drop down just a smooth node and play with the strength and maybe also the filter quality. And you think you can get a bit nicer results in here as well. So this is it for today. This is a quick video on how to quickly and easily create branching structures. I hope you like this. I hope you have fun playing around with this. And until next time, it's cheers and goodbye. And if you found this useful, please consider becoming a patron of ours. You get instant access to hundreds of additional videos and 2 new exclusive episodes each month. Massive thanks goes out to all our existing patrons. Without you, Antagma would not exist. Thank you.